Swayam Prabha. Digital India. Educated India.
Hello, I'm Anupam Saxena, an Associate Professor with Mechanical Engineering at IIT Kanpur. Welcome to the NPTEL course on Computer-Aided Engineering Design. This is the first in the series of 40 or so lectures. Here, through very simple examples, I'll emphasize how technology has affected the world around us, and especially a common man's life. I'll also try to underscore the importance of the interrelation between technology and computer-aided engineering design, or CAD in short. I've used a lot of sources, both books and the internet, to prepare the lectures. Many of these appear in the bibliography of the book that I co-authored with a senior colleague of mine, Professor Biren Sahai. These are the other three main sources I've used: Mastering CAD/CAM by Ibrahim Zeid, eNotes by C.K. Sheen, and the book on computational geometry for design and manufacture by Fox and Pratt. I have also used Google to borrow various illustrations I'll be using throughout the video course. Google uses different icons each day. This Google icon, by the way, is taken on the day of Sir Isaac Newton's birth, 4th of January. We'll start the lecture by attempting to understand the human psyche. Of course, we are not going to be discussing Sigmund Freud and his theories, in general, human psychology, but we are trying to find how human thoughts have shaped the technology from a cartwheel to an aircraft, from a pestle motor to a mixie grinder, from homing pigeons to email, twittering, from a plow to a tractor. Believe it or not, most of us must have thought about three fundamental questions sometime or the other in our lives. Question 1, who am I? Question 2, am I safe? And question 3, how can I make my life most comfortable? I call them fundamental because they relate very much to our existence and the quality of life we lead. Let's start with question 1 on identity. Who are we? What are our surroundings? And how do we relate to the environment around us? While who am I is more of a spiritual query, many brilliant minds like Galileo, Newton, Einstein, from much before and even now have engaged themselves in trying to resolve the questions pertinent to the environment we live in. In the micro scale, researchers have deciphered the atom, the very basic unit of matter. They have gone ahead into knowing the composition of the atom, namely the protons, electrons, and neutrons, and further the elementary particles that they can be split into. Likewise, we know now that life is composed of living cells, and the cells are made up of different subcellular components. In the macro scale, we now know that the Earth is a sphere and moves around the sun. The celestial bodies follow the laws of gravitation. Light can be dispersed into 7 different colors. It can bend due to gravity. Energy can be converted into mass and vice versa, and the universe is expanding. Many of these revelations are no older than 500 or so years. The gist? How inquisitive a human mind is, and past, concurrent, and future technology was, is, and will be a result of just that. The next question: how safe are we, and how can we prolong our lives, or maybe even defy death? Over years, human mortality has been a result of nature's wrath in the form of natural calamities, floods, earthquakes, tsunamis, a variety of epidemics like plague, influenza, smallpox, and tuberculosis. Humans have always desired to live long. It's painful to lose close ones. In recent times, a lot of efforts have and are being made to develop a variety of drugs, vaccines, to ward off different diseases and infections. Healthcare has tremendously benefited from technology. Cardiac failure, which almost had a 100% mortality rate, can now be averted and treated, both medically and surgically. Open and bypass heart surgeries have become sophisticated and much easier. Endoscopic surgeries, wherever possible, have hastened the recovery time. Imaging techniques like MRI, the magnetic resonance imaging, and CT scan, the computerized tomography, have made the diagnosis of complex neurological disorders more focused and efficient. In today's world, mankind needs to safeguard against itself. How ironic! More or less, all countries have well-defined defense programs. They're investing heavily to upgrade and acquire state-of-the-art defense capabilities. Tanks, aircrafts, submarines, traditional warships, and the modern ones having the capability of deploying naval aircrafts, semi and fully automatic weapon systems, communication, global positioning, all are a result of sophisticated technology. In fact, human life is regarded to be so very precious that even unmanned defense systems are in use or development. The drone bomber, for instance, can be remotely maneuvered and doesn't need active piloting. Most of us have already witnessed the notion of having a robot infantry in many Hollywood movies like Star Wars. Now for question 3. How to make life most comfortable? Let's see how technology influences a typical workday of our lives, from breakfast, bed, bath and beyond. Men and women both form the workforce of today's economy. Further, they need to work to be productive, useful to society, and to sustain their family. A person starts the day by brushing teeth. The two illustrations show the manual and automatic options. The manual one provides a nice morning arm exercise. The automatic one is possibly for those who are partly sleepy. Likewise, one has both manual and automatic options for shaving. Next, one hits the shower and gets ready for office. Typically around this time, one is in a hurry as he finds himself a bit short on time. He quickly prepares coffee and breakfast. How wonderful it would be for anyone to drive to the office in a Ferrari, the car, or a bike. Most of us, though, are content with standard family cars. Even then, numerous of them are equipped with well-developed safety features, entertainment options, and navigation systems. Or, if one is touring, he needs a mode of transport that can make him reach his destination within hours. A few within the country, more than that for a destination outside the country. Or, if someone is health conscious, he chooses to reside near the office and to bike to work. He reaches his office with his gadgets, the briefcase or the office bag, the cell phone and the laptop. Spends more than 8 hours of his day at work and comes back a bit tired. He comes back home, rests his feet on the table in front and catches up with what's going on in the neighborhood, the city, the state, and the world. If he has already not done that in the free time that he gets in his office, he catches on the weather forecast, sitcoms, and the movies, thanks to the modern day satellites that make these possible. And then he retires to bed. The punchline: technology is omnipresent in today's world. It is everywhere. An ironic observation is that technology is becoming more and more complex and involved in trying to simplify our lives. By the way, only a few of the available gadgets have been considered. Washing machines, dryers, air conditioners, phone handsets, vacuum cleaners, both manual and robotic, are a few of the many other examples. We shall now see how commonly used equipments can be different in design. Toothbrushes, they come in a variety of shapes, sizes, and are of varying curvatures. Both manual and automatic options are available in the supermarkets near you. The shapes and sizes of the bristles and the gaps between them vary. The head of a toothbrush can be composed of 2 or more pieces joined together by a flexible hinge, very similar to the one in a shampoo bottle. This allows the brush head to change its shape for better access. Even tongue cleaners are now available on the other side of the bristles. Next, shaving razors. Again, from a Swiss razor to an automatic one, many alternatives are commonly available. They come with multiple blades to give a smooth finish. In both modern and automatic ones, the shaving head is hinged to the shank to allow the blades to align freely with the curvature of the cheek. Shower heads. Many options are available in the hardware stores. Depending on how much time one likes to spend in the shower, options ranging from conventional single head to multiple heads or even wall-embedded multiple stream sources can be explored. The shower head on the right, for example, has multiple options, including one that provides a nice hot water massage. Coffee maker, toasters, and juicers. They come with different geometries depending on the quantity of coffee to be brewed, variety, for example, regular, decaffeinated, espresso, cappuccino, how many bagels or bread slices are to be toasted at a given time. Motorbikes. Pick one and go for a joyride or use it as a regular transport. Cars. Again, buy one that you and your family needs most. Choose from cool designer bicycles. Or if you are a big shot with a gigantic bank balance, you can go to work, buy your own private jet with a lavish interior or your own chopper. Who would not like to work in a custom designed environment? Laptops or personal computers. One can choose from many options available in the market. So is the case with the cell phones. In fact, there are so many that this picture describes the options best. Again, who would not want a custom designed home to come to, have a little coffee, chat with the better half, listen to the music of your choice, watch a movie on the television set you have chosen, dine, and then go to bed. Don't go to sleep yet, or don't get any ideas. Rather, save them for the next lecture where we'll try to design something. Let's consolidate on what we have covered in the previous slides. First, technology and product design appear to be synonymous. They are very strongly correlated. Technology cannot progress unless new designs are thought of. Then, about choices. Choices are good. A person can choose a product depending on what he needs. Here, need is a keyword. One can choose depending on what he can afford. Afford is the second keyword. Functionality, the third keyword, depends on both the need and affordability. Form, the fourth keyword, is the final design of the product, which depends on its functionality. Accordingly, a range of products are available so that the consumer makes the best possible choice for himself. Functionality and need are related. However, there can be minor differences. For example, a cell phone. One can have a wish list of numerous features. However, the associated cost will be very high, and the instrument will be affordable to only a select few. Even though the need or desire has no bounds, it is the affordability that acts as a check to the final list of functions or functionality of the product. We have briefly reviewed the term design as a concept. We are yet to delve into design procedure, but that's for later. For now, let's discuss how complex and intricate different designs can be. Let's consider the cell phone example again. Besides being a means of communication, when one is mobile, for which it was originally designed, the cell phones today can store contact information, maintain a task list, have features of a calendar, a calculator, an alarm, and a navigation tool via the GPS, the Global Positioning System. It can have options of playing radio, listening to stored songs, or as a camera. It can have a touch screen, can be used for texting, emailing, or for requesting stock quotes. You can even know the weather forecast, watch news, or your favorite sitcoms. As this list grew over time, the cell phones evolved. The basic cell phone design will have a display, a battery, an antenna, a keypad, and more importantly, a PCB circuit, which by itself is quite intricate. The circuit has a DSP, a microprocessor and control logic, memory, audio and video modules, and many other features that an electrical engineer would know better. Each feature by itself is quite complex and cannot be designed and tested manually. Further, different features can interact with each other. Sketching the circuit on paper and verifying each possibility by fabricating the respective prototype will be too time consuming. Alternatively, simulating the circuit on a computer is significantly simpler and efficient, as it cuts down on the manufacturing iterations. In other words, the design is mostly finalized in the simulation stage itself, and then is given a go for mass production. An airplane is an engineering marvel of the previous century. The basic illustrations show different parts of an aircraft: the wings, the engine nacelles, which are not shown in the figure but which are below the wings, the fuselage, the airfoil, which is the cross-section profile of the wing when different cutting planes are used. The ailerons are moved up and down for the plane to roll. The elevator is flipped up and down for the plane to pitch up and down. Rudder is used for the yaw motion. While we can understand the basics, what is more important is to realize how complex this engineering system is. Take a look at the cockpit, which has mostly all controls, enough to need not one but two pilots to fly a plane. And then there is autopilot, an automated system that assumes all flight controls when necessary. An aircraft can be regarded as a system of systems. While each system has specific functionality, the functions of a system can be associated with another. When this association is tight, when any one system fails, the entire design fails. A human body is a perfect example here. The design metrics or specifications of airplane-like systems are so strict that not any but a near optimal design is always preferred. By no means complex designs as demanded by today's world can be realized on paper. This is where computers step in. In a system of systems design, different systems can be identified and so can their functions be. For example, individual systems can be, say, system 1 with functions 1 and 2, system 2 with functions 3 and 4, and so on. Any system design can be performed as follows. First, a geometric form is given to the system and the design is modeled parametrically. By parametric is meant that the parameters of the system can be changed without altering its fundamental form. For example, a block has 3 sides and the length of each can be regarded as a parameter value. The values can be changed as desired without changing the basic shape. The parameters can be seen as the design variables. A given design, that is, a form with a given set of design variables, can be analyzed and its performance can be evaluated. If not found suitable, the parameter values can be appropriately altered to obtain a better design. In other words, the design procedure is of iterative nature. Most simulations are computationally intensive and are performed numerically. As a very simple example, consider the airfoil design. We know that the shape of an airfoil plays a vital role in generating enough force for the aircraft to take off and balance its weight when in flight. The contour shape is parameterized by means of a set of control points. Computational fluid dynamics, or CFD, is performed to analyze the flow pattern around it. The data is used to estimate the lift, say. The positions of the control points are appropriately updated to improve the lift. As a result, better airfoil shapes can be obtained. This illustration shows the airfoil contours at different cross sections of the wing of Boeing 737. In summary, computations involved in design are mostly demanding and of numerical as opposed to analytical nature. Iterations are handled better if automated through a computer. It is very uneconomical to prototype a design each time it is conceived. Instead, virtual testing through modeling and analysis is recommended. Let me corroborate this iterative design procedure through an example. Shown are the 2 rectangular design regions in the lower part of the slide. Black triangles represent fixed nodes. Green arrows represent the actuation forces. In the left figure, if we pull a point to the left, we require that the red node traverses an inverse tick path. For the right figure, if we push a point to the right, we need the red node to traverse a hat path. Both of these are challenging path generation tasks because of the kinks or corner points present in both paths. We are looking for appropriate linkage designs within both these rectangular regions. We do not know a priori how the linkages will look like, so we lay down the basic rules. We let both rigid and deformable members to be present in the linkage. we allow both fixed and hinged connections. The path lengths are large, so we allow the members to undergo large deformation. That is, we perform large displacement finite element analysis. The problem, therefore, is to obtain an optimal linkage topology or connectivity. First, we parameterize the design through a network of lines. Each line can be present in or absent from the layout. If present, the line can either have the characteristics of a rigid member, shown in black, or a curved, deformable member, shown in red. Further, nodes, that is, all the intersection points between the lines, can be repositioned. The shape and in-plane widths of a deformable member can change. Let's find out how the mechanism for the design on the left looks. Once again, the black members are rigid members and the red members are deformable members. Hinges are shown via the white circles. And now, how the linkage for the other design looks. Look at the way the cantilever is getting deformed. Both these linkages do pretty well in tracing the specified paths. The inverse stick path and the hat path, at least in simulation or in soft form. Both designs are non-trivial. It would have been very difficult for one to design such linkages through a paper-pen approach. One must note here that the form design is fully automatic. The obtained linkages are fabricated only once. And let's now see how the prototypes perform. The magnified version of the corresponding prototype in action. You could clearly see how the kink is created. One should realize here that these prototypes are exact replicas of the simulated designs. Notice how these mechanical linkages or rigid body linkages get logged to produce this kink here. The two examples here show the gist of how computer-aided design works. Scope of this course. There are numerous dedicated courses on analysis of different systems in the curricula of varied disciplines mentioned here, and many more. There is a course on structural analysis, computational fluid dynamics, electrothermomechanical analysis, PCB analysis, molecular dynamics, and many more. All these courses are numerical implementations. We will not cover them as a part of this course. Instead, we will focus on the three aspects of geometric design, namely solid modeling, modeling of curves, and surfaces. I have always emphasized on this phrase, learning by doing. I have encouraged students who have taken this course with me before on computer-aided engineering design to dirty their hands, because like many others, I also believe that unless one dirties his or her hands, she doesn't learn or he doesn't learn much. Following this slide will be a sequence of movies that I'll be describing to you or showing to you on projects that students in different batches have undertaken. They have fabricated virtually whatever they had wanted, and they had fun in the process. The first movie, Mailbot. This is a robot developed by a group of students to deliver mail or other paraphernalia from one office to the other. It is essentially a line following robot. Oh, something happened. Well, the robot takes a loop to turn now. Before turning, it drops the delivery and comes back. To learn CAD, one has to understand design. And the best way to understand design is to fabricate stuff. Try different things. Learn with the philosophy as to what doesn't work and what does eventually. Little magnified view showing different components of this robot. Motors, batteries, processors. This is another one developed by a single student entirely from junk to collect junk or to dispose junk off. Everything you see in this robot, except for the motors, is trash. Isn't that interesting? Looks like this robot is going to give competition to big companies. Of course, you can use this robot repeatedly. The third project, mechanical Bendix drive. It is an interface between the ignition and the engine in many automobiles. Whenever you start the ignition in a car or a bus, let's say, the engine doesn't start off immediately. It needs a bit of help, and that is what is provided by the Bendix drive. Let's see how. This is the mechanical version. So the basic philosophy is this. Upon ignition, a mechanical motor is going to be helping the engine out before it is on its own. In other words, before combustion gets automated in an IC engine. So that is the helper motor. This is the IC engine. The helper motor is going to be providing enough torque to the IC engine to aid in combustion. And then the helper motor is going to cease to function. Look at the mechanism closely. While the helper motor starts the engine, after a while, the shaft in the helper motor gets stationary, while the gear on it keeps moving idly. Somebody in my course got very excited. He wanted to design shoes to walk on water. Let's see if he got successful. Careful. It looks like he needs enough practice to walk on water. Getting better. A group of two designed a wonder clock. For them, it is not only noting time, but watching time is also fun. They do not want to take their eyes off the clock if it strikes a full hour. Some electronics, some mechanical engineering, a group of spur gears, and the front portion of the clock. Wait for the clock to strike 8. I do not in my class emphasize these projects to be new. These products can be very well established in the market. It is just for the students to open them up, dirty their hands, see what is inside, and if possible, try something new with the existing products. Isn't this beautiful? These two guys wanted to come to lecture theater and attend classes in style. They note it was summer when they worked on this project. Crazy and a lot of fun. They designed a hovercraft and they got so excited that they forgot to add a steering to it. People around these two also had a lot of fun. They used a heavy duty motor, a couple of hair dryers, amongst other things. The text would do the explanation. Let me tell you, I, as an instructor, immensely enjoyed this project, among others as well, definitely. They wanted to have an onboard battery, but just to demonstrate, they had a long wire. Let's see who gets the first ride. Seems to be working on the corridor at least. But the person maneuvering the hovercraft has to use his hands for steering. This is one of the DOMs we have here. Well, they successfully, I would say, successfully demonstrated the first working model of this hovercraft. Too bad they could not come to the lecture in style. I'm sure they will sometime. Next one, a group of 3 developed a Sherlock surveillance robot. What you see are views from 3 different cameras. Interestingly, a a cell phone is being used here to provide information to a remote system. You will notice that the three movies are not temporally coordinated, so there would be a bit of lag in the three views. Sherlock, Servet. This group of three seems to like Sherlock Holmes quite a bit. Using water as the driving propellant to send a vessel to space. This group of students believe in a clean, green environment. We got a lot of exercise done in the process. Is he pumping in air or playing a guitar? Some balancing skills. When would the countdown begin? Looks like they're just about ready. Okay, all for this much. 2 hexapods. Very simple robots, but I'm sure students learned something. They seem to have used a bunch of gears, motors, batteries. The process of assembly. like the hexapod is warming up. Okay, it's just about ready to race now. Uh-oh, it's moving backwards. Okay, slowing down. The second model. If I remember correctly, there was a race arranged between these two models. Who won is not important, but students learn quite a bit of stuff. This hexapod can turn. To conclude this lecture, it took a lot of time for Thomas Edison to design an incandescent bulb and figure how it works. In his own words, he did not fail about 4,999 odd times. Rather, he knew how the bulb will not work in those many different ways. If only he had used CAD, things would have been a lot easier.